the lecture. So in the previous lecture, what we did was to define the conformal symmetry, understand what is the conformal symmetry, what are the transformations, and we studied the irreducible representation of this conformal symmetry. Just to make a small comment, because I've been a little bit imprecise before, when we have an irreducible representation of the conformal symmetry, as I said, we have a ground state, which is the primary state. And because the Lorentz group and dilatation are, they commute the generator, we can simultaneously diagonalize both of them. So we usually define primaries to have a definite dimension scaling and definite spin. And then we construct descendants applying translation, the generator of translation. But to be very precise, when you apply p mu, you end up not with a definite spin state, but with the superposition of different representations. Because depending on how you construct the indices, you may end up with a higher spin or lower spin. So at any level in dimension, you will have increasing and increasing dimensions and different spins. You can have lower spins or you can have higher spins. So the primary state is definitely the state with the lowest dimension, but it might not be the, well, it won't be generically the state with the lowest spin, okay? Unless it is a scalar to begin with. In that case, you can only generate other higher spins or other scalars. But generically, if you were to make a plot in delta and the spin, let's say in 3 dimension, you start some primary state here, and then you create a whole set of descendants. Okay. And you can increase the spin or decrease the spin. Okay. This was to clarify what I said before. And another thing that I sketched before was the final form, the finite form of transformations. We define conformal transformation in infinitesimal form, but you can also obtain the finite form of the transformation. So finite conformal transformations will have the following form. X mu going to x mu plus a mu. Okay, this is trivial for translations. X mu going to lambda x mu for dilatations. X mu going to lambda mu nu x nu for Lorentz. This I'm sure you could have guessed yourself. But then the finite form of the special conformal transformation is slightly more complicated, and it's not very simple to integrate the infinitesimal form to get the finite one. And it looks something like this. Where is it? X mu goes to x mu minus b mu x squared, everything divided by 1 minus 2b dot x plus b squared x squared. So this is slightly more complicated. And one way to see that is that there are 2 ways. One way is using the a formalism that I'm going to introduce in this lecture, which is called embedding formalism. And then another more down-to-earth way is to realize that a special conformal transformation, even already at the infinitesimal level, can be obtained by composing a translation with an inversion. So an inversion, I, is not an element of the conformal symmetry, because it acts on coordinates by sending x mu to x mu over x squared. This is an inversion. So this transformation is not part of conformal symmetries. Nevertheless, it happens that if you compose the inversion with a translation and then an inversion again, you generate a conformal transformation. And so if you send x to x over x squared, and then you shift it with the translation, and then you shift it back, you obtain exactly this form. Okay. Of course, e squared is equal to the identity, so you can prove this simply proving that it's true at infinitesimal level. And one okay. If you have this transformation, you can show that the matrix G mu, let me write here. So under a finite conformal transformation, G mu, as we said by definition of conformal transformation, transforms like a factor omega square, G mu again. And omega for this various transformation can be easily computed. So in this case, omega is just 1. In this case, omega is lambda. In this case, omega is again 1. And in the special conformal transformation case, omega is this denominator. It's 1 minus 2b dot x plus b squared x squared. This will be useful later. So now that we have defined conformal symmetry, the conformal group, and irreducible representation, which is the action, we would like to understand how operators transform under this symmetry. And so we will see tomorrow, I guess, that given a state in your Hilbert space, you can associate to it an operator and vice versa. But for now, you don't have to think in those terms. You can simply assume that your theory is defined in terms of some operators, and those operators, because you have a conformal, you have a symmetry, can be classified in terms of irreducible representation of the symmetry, and you also would like to understand transformation properties under the symmetry. So transformation properties of operators. The first observation is that if you have an operator with which depends on the coordinate x, you don't have to. You can always use the information that you have about transformation property of the operator inserted at 0 to the transformation property at generic x. And the reason is that such an operator can be written as the exponential of minus px, operator inserted at 0, e to the px. Right? You can always do that. And therefore, the transformation property, meaning the commutation relation of an operator inserted at finite values of x, can always be of the transformation property of the operator with 0 argument. And the reason is that if you have a generator of a given symmetry G, and you take the commutation relation with OX, this can be written in terms of e to the minus px, the commutation relation of a new generator, G twiddle, which I will define in a second, the same operator, but now inserted at 0, and then e to the px. And what is the G twiddle? G twiddle is it's basically G twiddle is nothing else than e to the px g e to the minus px. And now you can use the Becker-Hausdorff-Campbell formula to expand this expression. So this can be written as a sum over n going from 0 to infinity, 1 over n factorial, x mu 1, x mu n, and then a set of nested commutation relations of the form p mu 1, commutation relation with p mu 2, and in the end you get G. Okay, so this might look very, very horrible, but if one, for instance, if one of the commutation relation of G with P mu n, if commutation relation of the generator G with P is proportional to P, you see that this object vanishes identically. So whenever the commutation relation of G and P is proportional to P, this truncated at very simple order. So, and this happens, for instance, if you remember the commutation relations, of course P commute with itself, D and P is actually P again. So after one step at n equal 1, this already vanishes. M with P, M nu with P rho is again proportional to P. So again, we are in this situation. The only case where this is not true is the commutation relation of K with P, which is, if you remember, is proportional to D. It's proportional to 2 d G mu nu minus M mu nu. And then in that case, you have to go to the second order in this expansion. But again, you will get commutation of D with P, which is P, and commutation of M with P, which is P again. And so you don't have to go beyond the second order in this expansion. So it looks ugly, but in fact, it's not very ugly. Yes? The operator where? Here? Yeah, sorry, the second one here is 0. Thank you. So This is to say that we don't have to worry about this commutation relation here. We can just define commutation relation for the operator inserted at 0, and then define the rest in terms of this formula. So we can restrict ourselves to operator inserted at 0, and the only thing we need to define for a given operator are the quantum numbers under the other generators, D, M, and K. So what I will going to do, I will define a commutation relation mu nu for an operator O with some generically, this operator can have indices, so I will call little r the representation of the Lorentz group in which it belongs. So this will be some representation, some r, mu nu, with indices, and let me collectively call capital I the indices. So this would be I, J, O, J, O, J, sorry, I, J, O, J. Okay, so this capital R is the representation of the generators mu nu in the representation capital R, and they have indices which are contracted below. So this simply specifies the transformation property under the Lorentz group, and similarly I will denote the commutation relation of OI with the dilatation operator delta O OI of 0. So I'm considering operators that inserted at 0 are eigenvalues of, if you want, of the dilatation operator and the generators in a given representation. And also I need to define what is K, what is the action of K mu on the operator 0. Okay, and again as before, here I have a choice. I can set this to 0 or I cannot set it to 0. If it's non-zero, then acting iteratively with K, I can decrease the dimension, but because I don't want representation of the conformal algebra which are unbounded from below, at a certain point I have to hit an operator which is annihilated by K. So the operator that satisfies this condition are called primary operators. Okay, and by acting with P, instead I will generate all the descendants. So this will be my definition of primary operators. Operators that when I take the commutation relation with K and O0, it gives me 0. Okay. And so now, using this relation, in principle, I could obtain the commutation relation for the operator inserted at any x. I will not do that, but it will be in the lecture notes, because it's not very important. What is important is to understand how the operator transform under a finite transformation, the one that I just erased. And what you can prove, and I don't have time to do that, is that if you have a primary operator, under a finite transformation of I of x in a representation of little r, under a finite conformal transformation, transform in the following way. You have a factor which is 1 over omega of x to the power delta, which is the dimension of the operator. Let's call it delta O. And then eventually the rotation matrix. Okay, so this will be the finite form of a transformation. Notice that this is a collective index. Okay, so if you have, I don't know, a tensor, two-index tensor, you will have the appropriate representation of the rotation. For scalars, if you're considering scalars, this object is simply not there. It's the identity matrix. You just have the prefactor. Okay. So now that we are equipped with this transformation property, we might start. We might want to study observables in a conformal field theory. So what are the observables of a conformal field theory? Well, because the S matrix is not well defined, as I mentioned before, a thing that you might be interested in are correlation function of operators. And because any descendant can be obtained from a primary operator simply taking commutation relation with P, or if you want derivatives with respect to P, with respect to the coordinate, then it's sufficient to understand the generic form of a correlation function of primary operators, because all the others can be obtained just by taking derivatives. So what I will study now are correlation functions of primaries. So I haven't specified yet what do we mean by operators and what do we mean by correlation functions. So for now, let's just consider correlation functions as defined in terms of a path integral. Okay, so this will be insertion in some path integral over your fields, the fields that define your CFT with some action. Here I'm being very generic. That makes sense. Okay, this is schematic. And there are several subtleties here that will be dealt with tomorrow. In particular, depending on which quantization that you're using, this correlation function corresponds to an order, time order, or whatever quantization order that you are using. Okay, so here let's do Euclidean, just for simplicity. Okay, so for now let's think in terms of a path integral where you insert a bunch of fields and this defines a correlation function. And what we would like to understand is what is the general structure of a correlation function which is consistent with those transformation rules. So the first example that I would like to consider is the correlation function of two scalars. So let's consider scalar phi1, which has dimension delta 1, and the scalar phi2, which has dimension delta 2. And, and we can ask, what is the generic form of the correlation function phi1 of x1, phi2 of x2? Okay. So, of course, because of translation invariant, this object can only depend on the difference. This is clear. Also, because we have a scaling variance, this object has definite scaling dimension. Therefore, this quantity here can only be something like 1 over x1 minus x2 modulus because of rotation invariance, and then the scaling dimension dictate something like this. And eventually, which I can set to 1. It's just a rescaling of the fields, okay? So let me set to 1. Now, this is, so far I've been using only translation, Lorentz invariance, and scaling, and dilatations. However, we have an additional symmetry. And this additional symmetry are special conformal transformation. So it's not very hard to see, I'll do in a second, that if you impose the right covariance properties under under special conformal transformation, the only possibility is that delta 1 is equal to delta 2. So special conformal transformation imply that delta 1 must be equal to delta 2. And if this is not true, then the two-point function of two scalar field has to be 0. So how do we prove that? Well, we just impose the right transformation properties. So let's see. So phi prime 1 of x1 prime, phi 2 prime of x2. This has to be equal to 1 over x1 prime minus x2 prime. But it also has to be equal to the transformed field. And the transformed field are related to the original one by that relation. So this is going to be 1 over omega of the special conformal transformation, which depends on x1 to the power delta, 1 over omega of the special conformal transformation, which only depends on x2 to the power delta 2, and then phi of x prime, phi 2 of x prime. Okay. And so because these two objects are factorized, so they only depend on a single coordinate, while the only invariant that we have been able to construct so far can only depend on a fixed combination of x1 and x2, it's not very hard to show that these two objects are consistent if and only if delta 1 is equal to delta 2. If this is not the case, then this equality cannot hold for any value of x, x1 and x2. Okay, so for two-point function, this is very simple. You can do it yourself. For three-point function of scalars, it's still doable, and perhaps I'll do it now. But if you start inserting in correlation function object with spin, then going on with this procedure becomes very, very quickly a nightmare. And so in order to overcome this difficulty, it's better to develop a different approach. Okay, just an example. Let me show you the form of the three-point function. So suppose now you have three fields, phi1, phi2, and phi3, each of them at their own point. And you consider the correlation function of this. Then, by doing the same exact logic as before, you can show that this object can only have a single form. So there will be one constant, which now, because I already rescaled my field in order to have a two-point function with a coefficient 1 in front. I'm not free to rescale anymore the fields. So now whatever constant will appear here, it has to stay there. I cannot rescale it away. And then there is a coordinate dependent function which is totally determined. And it looks like this. X12 to the power delta 1 plus delta 2 minus delta 3, x13 to the power delta 1 minus delta 2 plus delta 3, and then there is another term. Let me write smaller. Then there is a x, what am I missing? 2, 3. The power delta 2 minus delta 1 plus delta 3. Okay? So again, the form of this correlation function is totally fixed by imposing the right covariance properties under conformal transformation, except a constant, which see has a very important meaning. So is this surprising? Well, it's not very surprising. And the reason is, if you remember what we said before, whenever you have 3 points, you can always fix their location using conformal transformation. For instance, you can fix this to 0, 1, and infinity, which means that whatever you find on the other side cannot depend on the coordinate anymore because there is no freedom. So it can only be a constant. So this is to say that the three-point function are completely fixed by the symmetry. They don't contain any. They're fixed by the kinematic. They don't contain any dynamical information except for the coefficient in front. While two-point function instead are also fixed by conformal symmetry, But in that case, the constant can be reabsorbed in their definition. And x12 to the power 2 delta. Notice that because of this property of being diagonal in the space of dimension, we can always rearrange the fields, so we can rotate the fields with the same dimension such that this is literally diagonal, in the sense that if you have two operators with the same dimension, but generically they are different, you can rotate them and make it diagonal. This is possible in unitary theories. In non-unitary theories, it's not possible. Okay. So the idea is to develop a formalism that allows us to obtain these two simple results in a very straightforward way, and possibly generalize these results to correlation function of operators with spin, because in that case, doing this analysis is going to be a mess. And the way to do that is a formalism which is called embedding formalism. The embedding formalism relies on the observation that we did before, that the conformal group is isomorphic to SOD plus 1, 1 in Euclidean space. And we gave the precise mapping between the generator of the conformal group and the generator of rotation in 2 dimensions more. So the idea is to take this relation very seriously and embed our d-dimensional space into a higher dimensional space. That's why it's called embedding. So the new, so here we have the conformal group acts on coordinate in RD, and we're going to embed RD inside R d plus 1, 1. And in the new space, the conformal group will act very simple, in a very simple way, because there's just rotation in this space. But nevertheless, the mapping that I will provide between these two spaces will induce transformation on the original one, which are exactly the conformal transformation. And the way to do that is to consider the following embedding. First of all, let me introduce the notation. I will call coordinate inside the new space, RD plus 1, 1. I will denote them PA, not to confuse with the translation generator. Okay? There's a point in this space, and mu instead, x mu instead is a point inside my original space, Euclidean space. Okay? And the way to identify these two things is to consider, first of all, the following hyperboloid, which is identified by the condition that PA is equal to 0, and here I'm contracting indices with the metric of RD plus 1, 1. PA eta AB. Okay. This is a metric with mostly plus. So plus, and then 1 minus. Okay. So this condition here identifies an hyperboloid that I will try to draw now. Okay. So this is an hyperboloid, p squared equal to 0. And in this hyperboloid, I can also, so this of course is a codimension 1 manifold, so it's not enough to perform our identification, still too large. But in this manifold, I can consider, instead of points, I can consider rays. So a ray on this surface will be identified with a point in my original space. To make it even more precise, we can consider a section of this hyperboloid, which I will draw like this. Okay. So this section here is it's called Poincaré section. And is identified by the condition that A has the following form. Before giving you this form, let me slightly change coordinates and use light cone coordinates. So PA will be something like P plus, P minus, P mu, with P plus minus equal P d plus 2 plus or minus P d plus 1. Okay, so I will use this convention, light cone coordinates, and in this convention, this is, for instance, P plus, P minus. So the Poincaré section is a submanifold of this hyperboloid, such that P plus is equal to 1. Okay, and then the rest. So P mu, I can call it X mu, and P minus, because of the condition P squared equal to 0, has to be X squared. Okay, so a point on this red line is identified by a d-dimensional vector, x mu. Of course, it lives in a larger space, but it's identified by a single vector. And now we can ask ourselves how the symmetry, the SOD plus 1, 1 transformation act on this point. Nice thing is that because these are rotation in RD plus 1, 1, they act very simply. So the first observation is that the hyperboloid is left invariant, right? Because if I take PA and I send it to lambda AB PB, where this is a rotation, by definition, rotation preserve the scalar product. So under this transformation, the hyperboloid is invariant. This is good. So we have identified a surface which is invariant under rotation, so it's a good thing. The second observation is that the metric induced on the Poincare section is flat again. So the metric induced by eta AB. So this is a flat codimension 2 surface in this space. So this is good. We can because we started from R to the D, so we wanted to reproduce a flat space. Unfortunately, the Poincare section is not invariant under this transformation. Poincare section is not invariant, which means that, but the Poincare section was just a parameterization of the space of rays in this hyperboloid. So even if it's not invariant, we can rescale the vector that we obtain acting with the transformation to go back to the Poincare section. So to put it in formulas, we start from PA, which is defined, which is on the Poincare section, which is 1 x squared x mu. We act with the rotation. We obtain a PA, which is not in the Poincare section. So PA prime, let's say, which we are the form P plus prime, P minus prime, P mu prime, which is nothing else than lambda AB PB Poincare. And then we can rescale to go back to the Poincare section. So P prime on the Poincare section, A is going to be simply 1 over P plus prime PA prime. And this defines a new vector on the Poincare section, x prime square, x prime mu. And if you work out how x mu and x mu prime are related, you will see that these are literally a conformal transformation. So x mu prime is related to x mu by a conformal transformation. So this is very, very nice because we have, through this embedding, we managed to establish a relation between vectors in our original space through a rotation in a larger space-time. But the nice part is that rotation acts very simply, just matrix multiplication of vectors. And so it's very, very convenient to use this formalism to impose covariance properties. A nice exercise that you can do is to recover the finite form of conformal transformation using the embedding formalism. What you have to do, you have to use the definition of generators that I gave you in terms of the generator J. You remember we had this generator JAB defined in terms of the conformal symmetry generators. You can find which one generates the special conformal transformation, and you can see how x mu is changes under this transformation. And these generators are easy to exponentiate because they act linearly. So there are no problems with this. Okay. Are there questions about embedding? Yes. Point as infinity. You mean right? This is a special choice, okay? That you perform. You mean when I send x to infinity? Well, the point at infinity goes somewhere here. This extends all the way. But this is just a possible choice of this is a reference frame if you want. It's just fixing the point using conformal transformation. You can do that you can do the same thing here. You can send one point to infinity using, well, right. In order to achieve 1 here, you have to divide by the first component. So if the first component is 0, then that's the point that you, okay? It corresponds to some runaway there. Other questions? Okay. So in order to use this formalism, we have to define what our fields, how our fields in the original space-time R to the D are lifted when we go to the embedding space. The first so of course, because we are selecting a particular Poincare section, and we want our field to be defined on the whole hyperboloid. But if you remember, the Poincare section is not invariant, and every time you make a transformation, you have to rescale the vector in order to go back to the Poincare section. So if you have a function which is defined on the hyperboloid, usually you're not able to rescale the coordinate to go back to the original, to the Poincare section, because functions usually are not invariant under the scaling. So a convenient thing to do is to consider functions or operators that are homogeneous with certain scaling property under rescaling transformation. So we will consider function or operators O defined on our embedding space, such that let's see which O of lambda p A is going to be lambda to the minus some parameter delta, which depends on O, that, as you will see, will be identified with the scaling dimension of the operator in the original spacetime, O of P. Okay. So we're going to restrict ourselves to operators that have this property. This is not guaranteed, it's just it's a choice, if you want. And it's a convenient choice because in this way, once you perform a rotation and you go out of the Poincare section, then you can rescale the vector to go back to the Poincare section, paying the price of the rescaling. And nicely enough, if you perform this, if you make this choice, then you can define you can relate these functions to functions on the regional space. let's see how to do that. So for instance, for scalars, if you have a scalar operator living on your original space-time in R to the D, we will associate to it an operator capital phi, which depends on the coordinate PA living on the Poincare section, with this transformation property under rescaling, so that phi prime of P prime is going to be Poincare section. It's going to be 1 over P plus prime to the power delta phi of P Poincare section prime. Sorry. So the transformation property induced by induced by the embedding. When you rotate P in your embedding space, as I said, you go out of the Poincare section. So you rescale the vector in order to go back to the Poincare section. This brings out a factor P plus prime to the power delta. And it turns out that this P plus prime is literally the omega of X that we need in order to reproduce the correct transformation property of the field in R to the D. Okay, so with this identification, we can also reproduce transformation properties of fields in the regional space. Okay, so let me stop here for a second before going to spinning operators, and then we start analyzing the consequences of these transformation properties. Okay. So let's see a very simple application of this formalism. For instance, let's try to reproduce the formula that you obtain in D dimensions from the embedding formalism perspective. So we, as I said, for scalar fields, if you have a scalar field in our original space, let's make a table here. RD, and then RD plus 1, 1. Okay, we have a scalar field phi, function of X, and here we associate to this operator an operator capital phi, which depends on P, A, on the Poincare section. This PA on the Poincare section is uniquely determined in terms of X mu. So, and also this is homogeneous of degree minus delta. Okay, while this has dimension delta. And now we have seen that the correlation function of phi of X, phi of Y is 1 over X minus Y to the power 2 delta. And we'd like to reproduce the result from the embedding formalism. So we're going to consider correlation function of capital phi of P 1, and because I don't know yet that the dimension has to be dimension of the two fields entering have to be equal and approve it, let me consider two different files with different dimensions, okay? And then I ask myself, what are, so I have phi I with dimension delta I, with homogeneity properties delta I. And then we ask ourselves, first of all, what kind of invariance does this correlation function has to obey? Well, it has to be SOD, SOD plus 1, 1 invariant, which means that the only invariant construct, because Pi lives on the hyperboloid, P square is equal to 0. So Pi square is equal to 0. So you cannot use P1 square or P2 square. So the only thing that you can construct is P1 dot P2. Okay, if I get too close. Elevated to some power, and the homogeneity tells you that if you rescale either one of the two, this object has to be homogeneous of degree delta I, but because they only enter in this combination, if you have a power alpha here, and you rescale P1, for instance, here you get the P alpha. Here, from the field you get delta 1. If you rescale the other component, you would get delta 2, but here you will still get alpha. And this implies that the homogeneity property must be the same. So this argument was very similar to the one before, except that now the ingredients are SOD plus 1, 1 invariance and homogeneity. If you go to 3-point function, it looks exactly the same. So if you go to 3-point function, phi 1, phi 2, phi 3. Okay. Generically, there can be different structures. Again, you cannot use squares of the momenta. You can only use combinations. And so this property, together with the scaling, tells you that the only possible structure are this one, 2 times P3, alpha 2, and P1 times P3, alpha 3. And if you match carefully these exponents with the homogeneity properties, you will discover again that delta 1, alpha 1, alpha 2, alpha 3 are related to the dimensions of the three scalars in the way that we showed before. So I invite you to do this exercise. Very good. So this is, of course, this equation here is in the embedding space. So now you would like to go back to the original space, and a nice property that you might want to use is that if you work it, Pi dot Pj is minus 1/2 x1 xij square. So by using this relation, where xij, I remind you, is the difference. It's the modulus of the difference. Okay, so by projecting, of course, here there can be a constant, let me call it C twiddle in the embedding, 1, 2, 3. And this C twiddle can be related to the C 1, 2, 3 that I had in the original spacetime. So far so good. But for scalars, we don't really see the power of this formalism. The point where this formalism really enters, really shows his usefulness, is when we deal with spinning operator with spin. So let me try to generalize this approach. So and I will only consider a subclass of operators that are traceless symmetric operator. Okay, so these are tensors which have, let's say, L indices, mu1, mu and they are totally symmetric, and they're traceless. So if you contract any of these two indices, they give you 0. The reason I'm considering this will be clear next time, but they are the only important ones if you consider correlation, if you want to bootstrap correlation function of scalar operators. And also, these operators are present in any dimension, so it's a very generic thing to deal with. So once we have such an operator in ArcD, you want to lift it to the embedding space. The problem is, once you change the dimensionality of spacetime, the range of the indices changes. So naively, if you just take this operator and you match it with an operator, so the naive approach in which you match this operator to an operator A1 AL of P, it doesn't really work, because this object here has more components than the original one. So you need to project out a few components. So how do we do that? Well, the right way, it turns out that the right way to do that is to literally take an operator of this form and attach it a bunch of projectors, so that the resulting operator will be exactly the one that you started with. So this operation, this projection here, has been invented by Dirac back in the days. And so the right prescription, so at this point is really a prescription, is the following. A mu1 mu L will be equal, or will be defined in terms of an embedding operator through the projection dp A over dx A1 x mu1 dp AL dx mu L. Let me denote A hat, the operator in embedding space. A1 AL of P. Okay? So given an operator in the embedding space, you can multiply each index by this quantity here, and you obtain an object that has mu1, mu L indices, and you will call this object your operator living in the dimension. So you can perform a bunch of checks that this is a correct procedure, it's a correct prescription. First of all, one check is that if O hat is traceless symmetric. The same is true for O. Okay. And this is basically a consequence of let's see. First of all, let me give you the form of this object here. This object looks like 0, 2x mu, 2x mu, and delta alpha mu. Okay. So if you start with a traceless symmetric operator, you end up with a traceless symmetric operator, which is good. If you start with this does not alter. What do I want to say? Okay. Second of all, this projection introduces a sort of gauge invariance. So any component of a hat proportional to P is projected out. So all longitudinal components are projected out by this operation, which is good because it makes the counting of degrees of freedom correct. So if you have a traceless symmetric operator in D+2, it has a certain number of components, but because of, and this is a consequence of the fact that PA dPA of dx mu is equal to 0. So any component that is proportional to P is projected out. So you're subtracting all longitudinal components from this, and this turns out to give the correct counting. Okay. So with this definition, we can conclude that in order to consider correlation function of traceless symmetric operator in R to the D, we can start studying correlation function of traceless symmetric operators in the embedding space, and then we can just project out. We can just project down to R to the D with this operation. And notice that because of this second observation, we have a sort of a gauge freedom in choosing O. We can always subtract longitudinal components, and the result will be just projected out. So we can always restrict ourselves to transverse fields. So in conclusion, traceless symmetric operator in RD get identified with traceless symmetric and transverse traceless symmetric operators in the embedding space. A1 AL of P. Okay. And now we can ask ourselves, what are the correlation function of such an object? And this is answering this question in the original space is a nightmare, but in the new space is not that difficult. So let's make an example. So, one thing that we will need are correlation function of the form scalar spin L Okay, so what is the question is, what is the general form of a correlation function involving two scalars? Let's say they have equal dimension, for instance, and then do, let's see which example I want to do. Sorry, before doing this, let's do another example. Let's do an example of a vector. Okay, let's consider a vector v1, x1, and a vector v2 of x2. And let's ask what is this correlation function. And so according to this procedure, the vector is a traceless symmetric operator with only one index. So we can lift it to in embedding space to a traceless symmetric, well, to an operator with only one index. So tracelessness and symmetry are just trivial, but it has to be transverse. We can identify v1 of x, vi of x, with a vector in embedding space, just one index, and depends on coordinate. So this object is required to have two properties. It has to be homogeneous with scaling dimension delta v. So v hat of a of lambda p has to be minus lambda to the minus delta v. Let's call it delta I. V hat of p. And also has to be transverse. So if I contract v hat a of p with pa, it must give me 0. Okay? According to the identification that we made. And so now we can ask, in the embedding space, what is the most general form of correlation function of two such v's that obeys all these conditions? And this question turns out to be much easier. So let's see. Okay. So v1 hat a v2 hat b of p1 and p2. What is it going to be? Well, let me call this object GAB. GAB of P1, P2. For shortness, so the conditions on GAB are that GAB of lambda P1, P2 has to be equal to lambda to the minus delta 1, GAB, P1, P2, And similar story with P2. I'm not going to write it. And then it has to be transverse with respect to both coordinates. So P1 A GAB has to be equal to P2 B GAB equal to 0. Okay? And so, according to these conditions, we can write an ansatz, for instance. So GAB of P1, P2. First of all, let's take care of the homogeneity properties. So homogeneity properties tells us that if we divide by P1 dot P2 to the power delta, for instance, delta. First of all, the homogeneity already tells you that delta 1 has to be equal to delta 2. So let me call delta 1 equal delta 2 equal delta. Otherwise, you just get 0, just from homogeneity. And then we have to take care of the rest. So I will divide by a prefactor that takes care of the homogeneity property. And then here you have something which is homogeneous of degree 0. So it can only be ratios of stuff. And it has to be a two-index tensor. So the only thing that you have is eta AB or PA PB, P1A PB, P2B, and vice versa. So let me write like this. I will have a coefficient 1, the following combination, eta AB minus P2A P1B divided by P1 P2. And then eventually there could be a coefficient 2 contracted with the other combination that I have, which is P1A P2B over P1 P2. Okay, this is the only two possible tensors that I have. You can recognize that the term multiplied by C1 is transverse, so the only possible combination that can enter is this one. And also the second term is transverse, because P1 square is equal to 0, and also P2 square is equal to 0. But the second term is sort of longitudinal. So in the projection, when I project down, when I multiply this object here by dp over dx, the term proportional to C2 will be projected out. So I can simply forget about it. And so it turns out that only one combination is possible. So this is not very, very complicated. It's fine. It takes basically 2 lines to do this. If you try to do the same argument in 4 dimensions, you're going to get crazy. So this is where the powerful of the machinery enters. Okay, understanding transformation property in this space is much, much easier. And now, once you have this, you can project it down to the 4 dimensions, or sorry, to D dimensions, by multiplying, by contracting with this prefactor, and then using a bunch of identities. For instance, let me see if I have them somewhere. Right. So you have to use this identity here plus relate eta AB to delta AB And if you do that, you end up with a very nice formula for your original spacetime. Exercise. Prove that correlation function of v of x1 mu, v of x2 nu. Okay, now I'm taking equal because they have the same dimension, and so I can always diagonalize in order to have this two-point function diagonal. And so this will be 1 over x12 to the 2 delta, where delta is the dimension of v, times a tensor, which is the projection of this tensor down to d dimension, and it looks very something like this. Eta mu nu minus 2 x12 mu x12 nu divided by x12 square. Okay, it's not horrible, but still it would be very hard to obtain directly this equation. As an exercise, you can try to generalize this result to a correlation function of operators with L indices, and you will see that this combination always appear. Let's see if I have the final form. Okay. So generically, if you have operators with L indices, mu1, mu L of x1, nu1, nu L of x2, this will be equal to the same prefactor, 1 over x12 to the power 2 delta, and then you have a tensor which I will call I mu nu. Sorry, here the indexes were down. You have this tensor I mu nu repeated many times. Okay? So you have I mu1 nu1 times I mu L nu L plus symmetrization and traces. So, but these other terms are totally fixed by the symmetry and tracelessness property of the original field. So once you have written the first one, all the other will follow. Okay, so this is a very powerful result. You can show that two-point functions are completely fixed by conformal symmetry for this class of operators, and generically for any operator in conformal field theory. Two-point function is completely fixed. In a unitary theory, you can take the two-point function to be diagonal, meaning that two-point function operator will have a two-point function only with itself. And also you can rescale the operator such that it has a the two-point function has a canonical form with a factor 1 in front. This will be our choice for this course. Okay? Okay. In the final 15 minutes, I would like to compute another example, or at least sketch the proof, which is an example that we need, which is a scalar-scalar spinel operator. As you will see, it's also very simple. Okay, so the final example is scalar spinel. And in the let me just go to the embedding operators directly, and this corresponds to compute the correlation function of a scalar operator in the embedding space. I'm called phi of P1. For simplicity, you can take the same operator, phi of P2, and then with a hat, and then an operator O with L indices, A1, AL, depends on P3. And this phi is homogeneous of degree delta phi, and O is homogeneous of degree delta O. Minus delta phi and minus delta O. And in addition, O is traceless symmetric, and it is transverse. Okay. So now you can ask, what is the general form? Where can I raise? I can raise here. Okay, here it is. Okay, and so answering this question is slightly more complicated because you have 3 points. So the number of invariants that you can make start to proliferate. And also you have indices around, so it might be slightly complicated. So one trick to do this is to, instead of working with operators which have open indices, it's convenient to contract all the indices with some polarization. So you can, this is a generic fact, okay? And it turns out to be very useful in this kind of computation. You can always encode a tensor in a polynomial. And the way to do that, if you have a tensor, let's call it FA1 AL, you can contract all the indices with some polarization and define what is called f of z and the coordinate. Okay, let's keep it z only, which is simply f a1 al z a1 ZAL, okay? So generically, well, this can be done for any tensor. The nice thing about traceless symmetric tensors is that, first of all, because of both symmetry, this encodes already well, when you contract a tensor with equal vectors, you basically symmetrize implicitly. And also, if you want, the tracelessness can be encoded in this formalism by imposing tracelessness. Can be taken into account, if you want, by imposing that z square is equal to 0. Why? Because tracelessness means subtracting traces, so you have objects that are proportional to delta AB, but if you impose this condition, all these terms drop. And it can be proven that you can always pass from one to the other. Okay, I'm not going to do that, so you have to trust me. You can always recover by taking derivatives with respect to this polarization. You can always reconstruct the original operator. Okay, so instead of working with open indices, I can contract all the indices with a polarization, and in particular, I can choose polarization that square to 0, such that I implicitly take into account symmetries and tracelessness condition. Also, if I have an operator that has to be transverse, I can take into account the transversality condition by imposing that z times p is equal to 0. Okay? So one very convenient way to deal with indices generically, this is not only for conformal field theory, it's also if you have tensors of some global symmetry. A very convenient way is to contract all the indices and work with polynomials in the polarizations. So instead of studying this, I want to study O of P and Z, P3 and Z. Okay, with this notation. And then I ask myself the same question as before: what is the most general form of the correlation function that I can construct using the 3-point and the polarization now? Right? This object here will be a function g of P1, P2, P3, and Z. And the conditions are that P1 square equal P2 square equal P3 square equal Z square equal to 0, and Z dot P3 equal to 0. This is transversality. And on top of this, I have to impose homogeneity. Okay? So it's not very hard to convince yourself that there is basically only one combination that satisfies all of them. And this combination is the following. Also, if this object is spin L, you want G to be a polynomial of order L. So this has to be a polynomial of order L. It has to be L polarizations because they have to be contracted with L indices. Okay, so it's not very hard to convince yourself that there is only one possible combination that does this, and it's the following. So G of P1, okay, Pi Z can be written as let's see. So there is the usual prefactor, which is now slightly modified because you also have you also want homogeneity of degree L, if you want. So you have P12 to the power delta 1 plus delta 2 if they are different, minus delta 3 plus L. You have P23, you know where this is going, delta 2 plus delta 3 minus delta 1 plus L. And then you also have P1, 3, delta 1 plus delta 3, minus delta 2 plus L. And then at the denominator, there must be a corresponding transverse, corresponding polynomial. And you see that you can see that there's only one possibility, which is z dot p1 to 3 or p2 dot minus z dot p2 p1 dot p3 to the power L. Okay, and of course there can be a constant in front, some C1 to 3, C1 to L. Yeah. So no, it's sorry. Yeah. To everything. Yeah, you need to have L powers of Z. Okay, and Z can only be contracted with P1 or P2. Okay, and what fixes the relative, if you want, what fixes the relative coefficient here is the permutation symmetry under exchange of P1 and P2, because these are the same operator. Okay, and okay, this from here you can project down to the original space-time dimension and obtain the generic form of scalar operator with spin mu1, mu-l. If you want to open the indices, you can just take derivatives with respect to z, okay? And this will open the indices. So this will have a very simple form. Okay, there is the usual denominator, which I'm not going to write. And then at the numerator, we have a vector, which is 1, 2, 3, mu1. Minus traces. And this vector here, z1 to 3, is a vector constructed with the three components, and it looks like xik mu over xik square minus xjk mu divided by xjk square. So again, even the three-point function of two scalars and a third spinel operator is fixed in terms of a quantity which is completely determined by conformal symmetry. In front, there can be a constant, of course, because you don't have any freedom left to rescale operators, so this constant is actually physical. But the rest is completely, the coordinate dependence is completely fixed by conformal symmetry. As we will see tomorrow, this is not true for higher correlation functions. So if you have more than 3 operators insertion, this is not true anymore. Even if you have more than 2 scalars, more than one spinel, so let's say spinel, then the correlation function is not fixed in terms of a single tensor structure. There can be more than one, but still they're totally determined. When we go to let's say 4-point function, as we have seen this morning, you expect to have some freedom simply because you cannot fix the three points. You cannot be completely fixed using conformal symmetry. If you have more than 3, there are some conformal invariants, so generically you expect some determined prefactor times a function of this conformal invariant. Okay, I think I'll stop here, and if there is any question, I'll be happy to answer.